Thank you very much. So today I'm presenting Franklin, the machine learning RC car. So I've got Kendrick with me here today. So I'll just quickly cover what is Franklin. So Franklin's an autonomous car powered by machine learning and computer vision. So what will you get out of this talk? Basically, you'll get a deep understanding of machine learning and an insight into the hardware required for basic sorts of autonomous cars and driver aids. So there's not really a problem. We kind of made this car just for fun and something cool to do and kind of test our limits on what we can actually do. But this sort of technology does solve an actual problem. Every year, over 1 million worldwide deaths occur due to motor accidents globally. Most of them are preventable because they're caused by human error. So driving aids and autonomous cars are the way of the future when it comes to navigating roads. They stop accidents, help prevent deaths, because they basically take human error out of the equation. So a quick little bit about us. I'll let Kendrick quickly introduce himself.
So I'm just a first-year computer science and engineering student at QUT, and I like machine learning and computer vision.
I'm a first-year computer science student at QUT as well. I'm a hardware hacker. I love hardware. Not so great at software or hardware, but I like making them work together. Robotics, 3D printing, and drones are my favourite things at the moment. They kind of change all the time. My main recent project at the moment, that's good, natural language processing, which is basically trying to understand what humans are actually saying and let computers and software actually understand and interpret that. Home and car automation as well. I love automating things. It all ties into the robotics thing. And chatbots. So basically, I'm going to cover the hardware. As some of you know, hardware is hard. And hardware faults and intermittent hardware faults pop up all the time. And they're very hard to diagnose because they're intermittent or they have different symptoms. There's all sorts of different things can go wrong. And you can't just get out a quick little debugging tool and say, oh, there's a problem there, because it's not software. So I'll start off with the frame. So we have a remote control car, which is just a normal remote control car you might see a kid or someone driving around. We've started with a plywood platform. I've made lots of 3D printed parts to hold everything all together, and lots of hot glue to hold it all together. And to power everything, we're using LiPo and lithium-ion batteries. Some of you may know that these are not kind of safe, as you can see from that meme there. I'm going to say, though, they're generally not dangerous. They've got a really bad rap, just for example, like drones sometimes do. As long as they're managed properly, they're completely safe. I've never had one blow up. The reason we use them, despite these potential risks, is because they're light, high capacity, and have a very high discharge rate, which makes them ideal for robotics projects. I also use this remote control called an FR Tyrannus. It allows me to program in modes to do all sorts of different things to help when we're training the machine learning car. Also allows manual control when we want a bit of fun. So basically, these are the main hardware components. There's an Arduino Nano on board, and basically it's a hardware brain. So it talks to the NUC. It sends the steering values from the remote controller to the onboard computer, and that basically lets us record the steering inputs and individual frames so that we can train the model. It can also receive steering values and throttle values for when we're driving in autonomous mode, so it can act in both directions. There's also an emergency stop mode, as we had to use more than once. When you're driving around a yard in this remote control car that you're trying to train, sometimes it does silly things and drives off. So a kill switch there is really useful. And doing that in basically a hardware level is really useful. So there's two main power sources on board. There's the power source for the onboard computer, which is an Intel NUC, and there's also the RC car power source. Both of these are lithium-ion batteries. So the other difficult thing with using low-cost hardware, because we're uni students, is low-cost webcams are crap. They're terrible. They don't work well in bright sunlight. They don't work well in really dark areas. So we managed to get a Logitech Xenon 20 webcam, which is kind of a mid-range towards the high-end range of webcams, which is still only $100. Compare that to normal machine vision cameras, which are a few grand. They're very limited in terms of wide operating conditions. So we use these things called lens filters. They basically bring the conditions back into something that's a lot nicer to work with. So the first one we liked, so I made this mount because when you're putting these filters on, you need to change filters depending on what type of lighting and the situation. So in the middle of the day, it's really bright and there's lots of light, which makes it very hard for the exposure and all of the different settings on the camera to be set correctly. So when it's in the middle of the day, we put these filters on, and it basically is like putting sunglasses on the camera. But when we're training it in the late afternoon, where there's not very much light, the image is really dark and hard to see. So I made this little mount that you can easily take off. So the first type of filter is called a polarizing filter. Basically, really bright sunlight, and when things reflect off bright and shiny things, the light generally tends to become polarized, which is just basically a different, as you can see from the diagram, it's basically the light travels in a different way. So what the first filter does is it removes all this extra light that we don't want, which is all the reflections in the bright, harsh sunlight. So you can see in the two images, the one on the left is before the polarizing filter. The one on the right is after the polarizing filter has been applied. Just gives you a much nicer image to work with. A more stark example is here. You can see the reflections of the water. So the polarizing filter takes out all those nasty reflections and make the image a lot nicer to work with. I'll hand over to Kendrick to cover the software required.
So I'm just going to give a really, really high-level rundown on the software we use, which was convolutional neural networks. And so I want to firstly discuss the machine learning problem is whereby you have a function f of x, which outputs y, where f is the convolutional neural network and x is the image, and you're trying to label y. So this is really hard because images aren't depicted intuitively from a computer standpoint. They're arranged in a matrix format and consist of RGB, HSV, or YMC values, which are basically values ranging from 0 to 225 or 0 to 180, depending on the types it is. If you look at the GIF on the bottom left-hand side of the...
Right-hand side.
No, right, yeah. It's like, so 8 is really intuitive to us, but when depicted in image format, it's really hard to tell that it's an 8. And moreover, going back to machine learning being trying to model a function y equals mx plus c, for example, images consist of high dimensionality, whereby they consist of more than 3 dimensions. It's really hard to visualize it, but let's not try to do it now. Basically, we're trying to model a function of n squared dimensions, n squared being the rows times the column of the image. And this is really, really hard for several reasons if you ever tried to model a quadratic equation in 2 dimensions, but instead of 2 dimensions, you're doing it n squared dimensions. The complexity goes up like by orders of magnitude. And also, an image that's depicting a similar object can be can be depicted differently from different angles, lighting, and poses. And so, from the example, 4 images all show a cat, but it's a cat from different angles with different lighting conditions and different pose, which makes the image really, really differently when you view it from a computer's perspective. But luckily, in high dimension data, you can extract features from it really, really easily. So if you look at the top left-hand side of the picture, you can see that in 2D, if you're trying to separate out the red and green variables, it's quite impossible to compute a function which does that. But if you view it from 3D, you can actually create a hyperplane which separates out the images. It's actually really, really handy when you're trying to extract features from high-dimensional data. And so convolutional neural networks, they mimic how the brain works. So you receive an image, and it tries to build features, simple features, and gradually it becomes more complex and more abstract, which ultimately ends up to the object you're trying to model after. So for example, I got an image, and hey, there's lines there. Hey, multiple lines makes an ellipse. Hey, multiple ellipses makes a face. Oh, I got a face there. That's essentially how convolutional neural networks work. And so this is a really standard architecture for a convolutional neural network. It looks a bit daunting, but don't worry, we'll go through it pretty quickly, and it's actually very, very simple. And so I want to firstly discuss about the fully connected layer. If you guys were here before, I think Randall was discussing the artificial neural networks. This is essentially it. You have the fully connected layer is basically the artificial neural network, and it can be seen by a function y equals mx plus c, where y is the output, x is the input, and M and C is the hidden layers of it. So basically, you're trying to model the function with hidden input layers. Make sense? Okay. And so if you kind of combine several layers of these fully connected layers, you can kind of have a confidence interval depicting the confidence of this neural network modeling a function. So like the difference between the function you want to classify and the function you have. So it's like a confidence interval. So in this example, we have 4 confidence intervals: dog, cat, boat, and bird, which are all arbitrarily labeled. And it's pretty obvious that boat is the most has the highest confidence value in this, and the network will classify it as a boat. Also, going back to the convolution layer, basically a filter or a kernel in image processing terms strides through an image to produce a convoluted feature. It's really, really hard for me to describe it, so I think it's best if you look at the GIF at the bottom left. So you have a kernel, and it basically just goes through the image one by one by one, and it produces a new feature from the existing image. And the reason why this is done is because different kernels actually extracts different features from the image. So for example, that kernel would extract horizontal lines from the image, and that kernel would extract vertical lines from the image, 45-degree lines, 135-degree lines, and so on. But that's not just it. You could actually do blurring. You could do some sort of whatever you want with specific kernels, and this is why kernels are used in the convolutional neural network layer, the convolution layer, sorry. And so this is kind of like a live process of the convolution layer going This is a process of what the convolution layer goes through. And you have a feature map produced after each stride. And in reality, there's actually more than 2 feature maps being produced. That's actually 100, because you want to extract more than 2 primary features from an image. You want to extract as many features that depict the object you want to classify. So in reality, there's more than 2. Next, we have pooling, which again is really hard to describe, so I try to describe things visually. It's whereby you have the convoluted feature, and you're just trying to grab the maximum values from the convoluted feature. And the reason why it does this is because think of it as compressing the data dimensions. So you've got a 3D data set, and you're trying to compress it down to 2D without losing much variance. So as you can see from the picture examples above, you've got a 3D dimension, a data represented in 3D, and even after compressing it down to 2D, you still can retain the key features and the primary features of the data. And essentially what it does is it reduces a dimension, or n dimensions, and reduces compute time significantly. That's the reason why pooling is involved. And that's basically how a convolution neural network works. You convolute, you get features, you find the primary features, you get more features from the filtered layer, and you just rinse, repeat until you build up like an abstract model of something that you want to classify. So lines, shapes, simple shapes, complex shapes, a face. That's pretty much how a convolutional neural network works. And so TLDR, you extract features from the image and you classify it. And that's why it generalizes well, because it extracts primary features from the image, and then you classify not the image, but the features that it extracted. And so we'll show you a demo of what we went through while we're trying to debug the RC car.
So this first video is the first ever time we tried to run it. We had recorded a lot of data, about 20 minutes to 30 minutes of just constantly driving around. Either remote control, just manually driving around, and it was sending the values back to the computer so it could record them so we can train them later on. The training process took a little while, so we were very excited to see the first result, which was a lot less promising than we had liked or had hoped. And YouTube's trying to buffer. There we go. So we've just started it. It's coming along nicely and keeps going along. And that's where the emergency stop came in useful. So we tweaked a few things and added basically a multiplier value, and this was the second time we tried to run it. Sorry, did you want to add something?
And I shit you not, debugging the neural network was really, really hard, because essentially you're just chucking an input into a black box, and you don't know what it's doing. debugging was probably the hardest part of the entire operation. Not collecting data, not sanitizing the data, but actually debugging why it went wrong.
I don't know if you missed that last bit there, but you can see it was going along nicely. We were really happy, and then right at the very end, it decided to just keep going again. That's because the model wasn't generalized properly. In that specific corner, it couldn't recognize what to do, so it basically just kept going. That's the second time the emergency stop came in really useful, because it was about to run into that fence. And we've got lots of expensive things on there. So I'll play it again. We tweaked some more values, I believe. These are a few different videos chopped up. So we tweaked some more values, and basically it was running pretty well on the third time we tried. It ended up going 6 times around before it kind of ran off again. And you might notice up here in the top left-hand side of the track, it gets a little confused here. That's because I was being really lazy when we were training it, and quite often I was coming around too fast, so I cut straight through there. So the model then learned when it saw that type of bend to cut straight through the bend. Which is really, it's a good demonstration of what training affects a neural network. So basically, it literally learns exactly what you tell it. And you might have seen a few times it kind of started to turn and then went back, because I didn't do it every time. So it was getting a little confused. Try and go to the next slide.
Extra reading, if you want to look at it, there's TFLearn. I use TFLearn. It's a high-level API for TensorFlow, if anyone's heard of TensorFlow.
Just quickly, TensorFlow is a machine learning library that is made by Google, isn't it?
Yeah.
Yeah, that Google's released. It's really nice to use.
Yeah, and so the way we're doing it currently, it's currently considered naive. I'm looking into something called semantic segmentation. Don't know too much about that, but so I want to talk to that. Yeah. Yeah, and just something to think about. It's like, so this is by some guy from Reddit. It's like the latest and greatest technology will not change the world, but the greatest and latest technology from 5 years ago, made commercially available and cheaply, will change the world. And this is what I think is happening with neural networks and machine learning currently.
So that's just some details in the first version. We decided it'd look cooler without the car because you could see all the cool things inside of it. Unfortunately, we don't have a track available, so I can manually drive it around to quickly show you that it does drive around. And this isn't turning on because it's not plugged in. Give me a second.
I'm just going to grab my laptop to show you guys what it visualizes when it's actually predicting outcomes. Like 2 minutes.
All right. So this is my remote control I was talking about before. So this is just me manually driving it around, which is really useful when we were training it, because as it's driving around, the Arduino is actually sending the steering and the throttle values back to the onboard computer. So when we're running the training program, it can actually record those values and match it up with the frame. So we did want to get it running quite fast, but we didn't have much time to actually implement everything and test it. But hopefully with some more training data and more revisions of the actual model, it's a very ambitious goal, but we would like to, on a bigger track, get it to drift around corners. We think that's entirely possible. The frame can pretty much definitely do it. And just with a lot of refinement to the model and a lot more training data, we think it's definitely possible. Kendrick's just loading up his laptop there. So just lift it up so you guys can see. I don't know if there's a document camera. It doesn't really matter. But that's the onboard computer. It's just an Intel NUC powered off the power bank. That's the webcam mount. And yeah, afterwards, we're finishing a little earlier so you guys can come up and ask questions and have a look if you want. Kendrick is just going to show you this video quickly. And then that'll be it. And yes, this is a fancy controller.
What's this one? Okay, so this is essentially what the data looked like while it was being collected. And so, like the green line just dictates where it's going to turn, so left or right. And so we collected a bunch of data, labeled it, and had to sanitize it and see, hey, is it collecting right data? At one point, we were receiving data that was 5 seconds late. So we realized we had to trash all the previous collected data because of some hardware issues with he can explain it.
It was a little annoying. So what the Arduino was doing, it was spamming as quickly as it could the signals it was getting from the steering wheel, from the steering controls. But the software program that was actually learning this data couldn't keep up with it, which meant it kept getting delayed and stuck in what's called a buffer. So what we did was we both made small changes to our programs, which meant every time he wanted data, he would actually ask the Arduino, the microcontroller, for that data. And then the Arduino would respond with the data that it wanted. That meant it had it instantly, and there wasn't any delays with that. And then that's the first model we trained. And then after that, we fixed that little issue. The model came out pretty perfectly.
And this is like a visualization of what it does when it's predicting. Hope it loads. Yeah, and so the green line's what it's actually doing, the blue line's just, hey, I should do that. And you can see it's not really 100% accurate, but it does fluctuate from time to time.
In simpler senses, I can't remember which one's which, but one of those is what I'm doing to steer it, and the other one is what the computer thinks it should do.
Yeah, and...
so the green line is me, I think.
Can you guys see it?
Yeah.
Yeah, I should maximize it. Can I maximize it? No,
Probably
I can't. Oh, well, yeah.
So just with more data that we collect, if we put a lot more effort into collecting more data, the more data we collect, the more it can generalize. So you can see it's a bit glitchy, a bit buggy. It works well enough on this track at low speed, but basically the more data we record and give it, the better it can get and the better it can learn. I think that's about it.
Yeah, that's about it. Oh yeah, and shout out to Fastmail for providing us with two-factor authentication keys. So if you want one, get it from Fastmail. Yeah, that's about it. Thank you.
So we've got a couple of minutes left. We tried to finish a couple of minutes early because we thought there might have been questions. You're more than welcome to come up and have a look as well at the car and the hardware. I've got it here, but otherwise, thank you very much.
Okay, thank you to you two. Oh, there's a question. We've got a little bit of time. You may as well.
I was just wondering, how does, like you train it on that track, does that only teach it how to drive that track, or can it be adapted to other situations?
So yeah.
For now, we're not sure because it gets chucked into black box, but if we train it in different conditions, then it most definitely will be able to drive at different tracks. Fun fact, NVIDIA recently released a paper for its self-driving car, and it's almost the same technique as we're using, but the technique we're using isn't really like original. It was kind of collated from different papers.
So basically the short answer is we're not too sure. More data will mean yes. But at the moment we're not entirely sure. Yep. I think the answer to that is pretty much all of the above. Much better hardware. They have very, very large, beefy computers running their cars. They also have a multitude of different sensors, like I've got this one. I've also got, they also use this thing called LiDAR, which was mentioned earlier in another talk, which is just what they do is they spin this laser around really, really fast, and it creates a 3D model, and that lets them do a lot more accurate things than just vision. So we're using just basically images. So they've also got sonar sensors and a whole sort of different sensors are all integrating into one package. So theoretically, if we integrated all those sensors and if we had a big team to make similar algorithms that they made, then yeah, we definitely could.
Okay, so that's all we've got time for. Once again, thank you very much to you.